All right, so for mean value theorem, we're going to explore this idea using our calculator. So the first thing we want to do is graph our function in number 1. We have our function is equal to 1.2t sine of t. Now, we don't use actual t's in our calculator, right? Just all x's. Okay, so I'm going to go ahead and type in 1.2x times the sine of x. And this one specifically tells you to sketch it on a certain window. And we know how to change our window settings, yes? Okay. So it tells me my window settings are x is 0 to 2 and y is negative 1 to 2.5. So before I even hit graph, I'm going to go to my window settings. And I'm going to change my x to be 0 to 2. And I'm going to change my y to be negative 1 to 2.5. Now, one thing it doesn't actually say on here, but I want you to notice on the graph itself. Can you tell what the scale is? What are they counting by? They're counting by 0.5s, right? On the graph on your notes. Do you see the 0.5s in there? So I'm going to go ahead and change my scale as well while I'm in here. It would be nice for me if my graph lined up exactly with what I'm trying to graph on my paper. So we're going to go ahead.
Wait, why is your scale like?
Look at the graph on your paper. And they have like slash marks at 0.5s. Okay. So I'm going to go ahead and change all of that stuff and then hit graph. And I get that loveliness. All right. Now, we did not read like the stem of the question, but let's do that now. This function represents the distance in meters of what? This is the distance in meters traveled by a turtle over the first 2 hours of a trip. Okay, so our turtle has traveled this lovely distance. Okay, so what in this case do you think the x-axis represents in that word problem? What's t represent? Time. Which we're measuring in what?
Seconds. Oh, minutes.
Hours. Okay, because it says over the first 2 hours of the trip. So part 1, the x-axis represents time in hours. Therefore, what does the y-axis represent? Okay, distance in meters. Okay, and you sketch your little graph in there to make it look like this. Okay, I can't really because I'm kind of off to the side, but you will sketch yours in. If we would like to find the average velocity of the turtle for the entire trip, what's the average velocity in terms of like what we've been doing?
Average rate of change.
It's like average rate of change. How do I do average rate of change? Okay, well, we would do, in this case, we're using S of t. So how would we show my setup for this?
S of 2.5.
S of 2, because we're going over the first 2 hours, minus S of 0 over 2 minus 0. Now, how do we do that in our calculator? Okay, go back to the calculator part. Because it's the distance over the first 2 hours of the trip. The x is going from 0 out to 2. So average rate of change is from 2 to 0. Yeah? All right, so we're going to go back to our calculator.
My calculator is giving me an error when I do y2 is 0.
It's not y2. It's y1. All right, so we're going to go into our calculators. And we're going to use our fraction and do y1 of 2 minus y1 of 0 over 2 minus 0. And no matter what it says, because it will always say be accurate to 3, we round to 4. Therefore, the average velocity of my turtle over the entire trip is 1.0912. What are we measuring in? Meters per hour. Good. All right, so then if I want to find the average velocity for the first hour of the trip, how do I change what I've just done? I do S of 1 minus S of 0 over 1 minus 0 or 1. If I'm doing this on a calculator section of my test, do I waste my time over 1 minus 0?
No.
I do not, okay? I might write it on my paper to show the correct setup, but I would not actually type that in, okay? So then we do the same thing on our calculator for that one. If I am going to save myself time, what do you think I'm going to do since I just did this?
You can go above and
Yep. We go up, use that setup, and go up, and literally all we're changing is 2 to 1, and that 2 down here at the bottom to 1, and it spits out my new average velocity. Yep. So 1.0098. All right, so average velocity is 1.0098 meters per hour. All right, on your graph, draw a line segment connecting the points. A is 0, S of 0. Where is that on my graph? 0, 0. And B, S of 2, or 2, comma, S of 2. So what I'm doing on my paper there is I'm going to, and since I can't show both graphs at once here, I'll do it on the calculator part here. You are drawing a line segment connecting from here to here. Yes?
How would you write that in your calculator?
You can do it in your calculator, but we really don't have a need to do it. Okay? I don't want you to get hung up on like things that you don't actually have to be able to do. Okay? Okay, so what does the slope of that line represent? Average velocity from where to where? From 0 to 2, right? Okay. So we are going to say that is our average velocity.
How do we know that?
Because the slope of that is the slope that we found in part B. Right? Alrighty. Now, here's the tricky part of this and where we're actually going with mean value theorem. We're all okay with average rate of change, average velocity. All of this stuff is not new to us. On the graph, the next thing we want to do is draw a line tangent to your curve where you think that line would be parallel to this one. So if I'm looking at this, I'd like to draw a line that is parallel to this one that's just tangent to the curve. Okay, where do you think I might be able to do that?
Go through like kind of like the math self-control.
Okay, I could go through somewhere like there-ish. I'm kind of bad at drawing these because they never end up being parallel, but that's kind of the idea there. We want to draw a line that might be tangent right here that is parallel to it. Is there somewhere else that might happen? It might happen at the bottom in here, right? Okay, do we see that that's possible for that to happen in both places?
Yeah.
Okay. So if the blue line represents our average velocity over the entire trip, what does the slope of these tangent lines represent? Instantaneous velocity at those specific points, right? So that's our part H. Instantaneous velocity or rate of change at whatever x value that is. We don't know what that is right now. Okay? So what we can conclude from this in part I. Our conclusion is that on this interval, there is a point, maybe even two of them, where f prime at that point is equal to your average rate of change over the interval.
Wait, where are we writing?
This is part I. I don't want to lose my graph, so I'm not moving it. Okay. Are we all okay with that conclusion? There is a point on this where our instantaneous velocity is equal to our average velocity.
Yeah.
At least one for this particular graph. Okay. All right, so let's look at another example of that then on the next page. Yes?
The point of 10, see,
Mhm.
would that just be those two lines that we just drew?
Yep.
So both lines could be labeled C.
Yes, we could label either one of these C, S prime at C,
Why?
because we were using S of t, not F.
So G, where it says labeled as constant.
Yeah, it should say,
It should say prime.
yep. Oh, no, excuse me, it should not say prime, S of C. I'm still using S, I'm not using F of, because we're not using a function F of. All right, so first thing we're going to do in second part on page 72 is we're going to graph the function given to us over the particular interval, okay? So we're going to go back to our calculators. We are now on page 2. And we're going to clear out what we have in our calculators, and we're going to type in our function. Did I tell you guys that I found a shorter way to find the fraction boxes? It's alpha x. If you didn't know that, shorter way. If you use alpha x.
Oh, wow.
I know. Someone else told me that. It's not working on mine right now, but it does work.
No, it does work. I just
Yeah. I don't know why it's not working on mine, but there it goes. Alpha x. Nah, it's just laggy is what it is. All right, so I've got x squared minus 16 over x squared plus 5. All right, now this one also has our interval on it. So before I hit graph, I'm going to go to my window. This time I want my x's to be from 0 to 3. And I'm still counting by 0.5s there for the x's, yeah? The y's are not counting by 0.5, so we'll look at that in a second. We'll look at the graph on your paper.
They're counting by 5.
Yeah, they're counting by 5s. So if you want it to be accurate, it's good to look at the graph that you've been given. The y's are counting by 5s on this graph, so I'm going to change everything to match what I've been given here so that I can sketch this. And I get that graph. All right, so now that we've walked through the first problem, I do feel like you are probably able to do parts B through, I don't know, do B, C, and I don't know why it skips to F. F, G goes back to E. I don't get it. But anyway, I didn't type these. So go ahead and do parts B and C and the next one after C. I'm going to show in part C, I'm doing the slope as f of 3 minus f of 1 over 3 minus 1. And we know how to find those slopes now, yes? Okay, so take a minute and find that slope. All right, so my slope came out evenly to 64 over 9. Did we all get that?
Yes.
Yeah, if you get a fraction, like that's obviously going to be more accurate than a decimal. So let's go ahead and write that down.
Oh, so you don't want us to write the decimal?
Not if it's a nice fraction, no. Nope. So I've got f of 3 minus f of 1 over 3 minus 1. This is always going to be more accurate in the end. All right, so I've got 64 over 9. Now, on the graph above, we want to draw a line tangent to our function, which is parallel to the segment. Again, this is a guessing thing right now. Okay? Yeah, it's somewhere in that maximum part. So if I have my line drawn here, I have got, my segment connecting my endpoints. If I had to guess, I might say, okay, I can draw a segment there-ish. That looks a little bit too steep. So maybe here?
Sure.
That looks decent. That's pretty good. It's better than when I tried to do my hard copy of my notes because I drew it in pen and it was like, this is the worst one ever. But oh well, I did it. Okay, so if we have truly picked the right point, okay, let's say this is 0.5, 1, 1.5, like 1.6. Would you say that's like 1.6-ish?
How do we know, like, on this, like, test, like, what if I don't?
We're getting to the place where we know specifics. We're guessing right now. We're just building a concept. You will not be guessing. Okay? Are we okay with that x being about 1.6?
Yeah.
Okay. So in part G, the derivative, we're going to say f prime of 1.6. If that line is truly parallel to this one, what is f prime of 1.6 going to be?
7.9 or 64.
64 over 9. If I've truly picked the right point, we're saying that instantaneous slope there is the same as the average slope here, yeah?
Yeah.
That's if I've done it correctly.
Because there's
Yes?
parallel lines,
This
the
is
slope.
I'm not
Okay.
about, like, everything else.
Because it should be same slope. Okay?
Because derivative is basically just the slope. So
It's the
that's
slope at a specific point, yep. And so what we're doing over the space of all of the stuff that we're working on here is we are trying to get to the place where we have an accurate f prime of x being equal to the average rate of change. That's where we're working towards. This is what the mean value theorem is. Okay? Now, there's sometimes that this does not work. So let's look at some instances where it does not work. These we're going to go a little bit quicker so that we don't have to spend all the calculator time. Okay? All right, so on the next page. We have a graph here, and I'm going to eliminate my calculator for a minute if I can. All right, so let's just take a look at this without looking at our calculators, because this is not a calculator-defined function for us, okay? If I drew a line segment connecting my endpoints on this particular graph, okay? So on this graph, drawing a line segment connecting my endpoints would look like this.
this isn't going to work though.
Okay, why do you think this is not going to work?
Well, because there's two different lines that have different slopes.
Okay, these have different slopes. Now, it's okay to all have different slopes. The other graphs we did had different slopes. The slopes were changing.
Well,
But
one's
is there a
positive and
place
one's-
that you think you could draw this?
Oh, wait, no, that's his, fine.
Right. I want to try to like draw it down here or like in here somewhere, but it's probably not going to work because probably what's happening in there is we're not getting to a place where it's actually accurate. Okay. So is there a place? Well, no. And the issue is, Mike already picked it out, this right here, does that have a derivative?
No.
No. So if any part of your function is not differentiable, this whole concept falls apart. Your average rate of change is not necessarily ever going to be the same as your derivative. It might never happen if you have some non-differentiable spot in the middle of it. Okay? Now, without our calculators again, let's talk about the graph below here. We know how to graph these functions. What are those?
Oh, that's the first,
Okay.
yeah.
This is our prereqs, right? Okay, this is a rational odd function. Where does it have an asymptote? At 2. It has a horizontal asymptote at 0. Where are our two branches? Usually.
Top right and bottom left.
So this is a function that we know and recognize. It looks like this. Okay. We want this function only defined on the interval 0 to 5. So I'm going to erase that section. Okay. So 0 to 5, and I'm going to 1, 2, 3, 4, 5. We'll cut out this section too. If we drew a segment joining the endpoints here,
We'd have to have 2.
that would be, these are my endpoints. Okay?
Oh.
Because it's f of 0 and f of 5, right? So we have a point here at 0, f of 0. And we have a point here at 5, f of 5. Right? Now, logically speaking, look at that. Is there anywhere I'm going to be able to draw a line parallel to that?
No.
There's nothing even close on this one. We like the last one we tried to like find a place. Is that going to work? No. But again, okay, that one up there had a point where it was non-differentiable. What's the issue with this one?
There's nowhere you can draw it.
This function, it's discontinuous.
Oh my
Oh,
gosh, you guys
great.
did it.
There you go. So these are problems that make the mean value theorem not apply. One is not differentiable. One is not continuous. So the answer to part B is no. We don't have a place for that. Okay? Differentiable means you can take the derivative. So this place right there, we can't take the derivative where there's a sharp turn, right? Okay? All right. So let's finish this up on the next page. Yes?
So because it's not different.
The mean value theorem says if y equals f of x is a continuous function defined over the interval a to b, and f of x is a differentiable function. In other words, we can take the derivative on that interval. Then there is at least one place, C, at which our instantaneous rate of change is equal to average rate of change.
Connecting those
Math language is so weird.
I know it is. Okay, so it's it's the endpoints. Yep. So A and B are your endpoints. So it's always going to be the average rate of change over the full interval that we're looking at. There will be a specific spot where we can take the derivative and say that that instantaneous rate of change is the same. Okay? All right. So let's just use a basic idea here. Let me give you y equals 2x cubed minus 3x squared plus 1. And we're going to look at this on the interval. Let me give you nice numbers here. -1 to 2. So we're going to show that there is at least one place where the derivative equals the average rate of change. So two things we need to be able to find right now.
Just factor.
We don't have to factor this because this is not the what, right?
Oh.
We want to prove the derivative at a certain point equals the average rate of change at a certain point. Yes? Okay. So I need to find two parts to this. First, how do I find average rate of change? We do y of 2 minus y of -1 over 2 minus -1 turns into a plus. Okay, and if you don't want to show a lot of work for this, this is the safest place to go. Immediately show me average rate of change setup equals what on the left-hand side? The derivative. Okay, what is the derivative?
6x squared minus 6x.
Okay. So I show my setup. Immediate derivative equals average rate of change. Now, before I can do any actual work to solve this, what do I have to do? Plug in the values. All right, so take a minute. Y of 2 is going to be 16 minus 12.
Five.
Plus 5 over 3, so 3.
So 5.
So what did we get when we plugged in y of 2?
5.
4.
Huh?
Wait, 16 minus 12 is 4. 4 plus 1 is 5.
Okay. Yeah?
Oh,
5.
I forgot the 1.
-1, it would still be -2.
-2
Plus.
minus 3.
But
Yeah.
it would really be plus.
No, because the -1 squared is going to be positive.
No,
Yeah.
I can't do- 0?
So that's going to be -2 minus 3 plus 1 is -4. So plus 4 over 3. Yeah?
I tried to outsmart you.
All right. So now I have 6x squared minus 6x is equal to what?
3.
3. Now, I have no idea if this is actually going to solve out because I'll be honest, made this up on the fly. Okay? All right. So if I need this to solve, what do I do? With 6x squared minus 6x equals 3. In order to factor it, I have to do what? Set it equal to 0. So 6x squared minus 6x minus 3 is equal to 0. What do we do to factor?
You can take out a 3.
Take out a 3. Gives me 2x squared minus 2x minus 1.
And then factor.
And you'd factor. I don't know if this is actually going to work for factoring. I don't believe it will. No. It won't, but, I tried. Tried to make it work. But that gives you everything but the easy part of the answer, right? And you would just say whatever x values fell within the interval I gave you, that's where that happens.
I think it might work.
That is not
No, it
factor.
doesn't.
That does not factor, I know that, but I'll back it up and find an easier way before 7th period tomorrow. Okay? Now, the last things to finish up with, there is a specific version of the mean value theorem called Rolle's theorem. You do not need to know this by name because you can easily apply mean value theorem to it, but it's good to have at least heard it at least once so that you know it's a thing. Okay? Rolle's theorem says if your endpoints have equal y values, if their y values are equal, what's your segment joining them going to look like? It's going to be a horizontal line, right? Because if you're going from A to B and you have equal y values, the line joining them is going to have a slope of what?
0.
All right, so then it follows that there is at least one number c on that interval at which f prime of c equals 0. Well, it's shocking. That's just the same thing. It's the slope is equal to the derivative at that point, okay? Now, I had put one down here, but let's look at this example for us. F of x equals x cubed minus x squared minus 2x. And we are going to go on a very specific interval because I needed this to work out. And it's the interval 0.445 to 1.8019. Okay. So if I want to prove that there's at least one point of this, it's the same setup as before. What setup did we say we do?
We plug in the values.
Okay, we do f of 0.445 minus f of 1.8019 over 1.8019. Ooh, yes, thank you. Well, it doesn't matter. I could do it this way as long as I do it the same on both. Slope doesn't matter as long as you start and end with the same one, right? And that has to be equal to what? F prime of x, which in this case is 3x squared minus 2x minus 2. Okay? Now, if you want to do those f ofs with those lovely decimals, you are not going to type them all into your x's. What are you going to do?
You're going to put that in your y1.
Yep, this is going to become your y1, and you're going to use your y1 notation, yes?
Your x to the third.
Mm-hmm.
Minus x.
Yep. Now, I don't know whether this will work out exactly, because like I said, I rounded off decimals, but essentially this is going to work out to 0.
Dang it, why on my calculator does the hack not work?
It should.
It doesn't work on mine.
Mine doesn't work either.
Sometimes we can update your operating system on those.
Bully.
All right, so we do our slope. It equals 0.
Yeah.
So
Because I have 6 minutes left, I'm speeding through that part. You solve by factoring. Okay? So we're looking at 3x and x, factors of 2. I gotta have, is that gonna work?
No, that doesn't work.
Ooh, how else could you solve it?
Quadratic formula.
Yeah. You could solve that with quadratic formula, but honestly, you'd have a calculator for this part. So what's easier than quadratic formula?
Plug it in and see where-
Graph that and see where it hits the x-axis. Okay?
good graph.
Mm-hmm. Graph and find x-intercepts, right? Because that's the same as we've been doing in this unit. This is the derivative. We want to know when the derivative equals 0. This is critical numbers, right? Same thing. Okay? Now, before we leave for today, because I trust that you know how to do that part of it, I want to go through the next page of big theorems for you. Because at this point, we've hit 3 big theorems. And this is a very nice summary page for you to remember what you need to write for each one of them. Because, you know, we all kind of forget. IVT's been a minute, but it's here. All right, so big theorems, things we need to know. The first one we did this year was intermediate value theorem. In order for us to use intermediate value theorem, we must know the function is what? Continuous. Okay? So if we know that it's continuous, the shorthand version of IVT is that f of x passes through all y values between f of b and f of a. In other words, if we have here to here, we know it passes through all values in between. Yeah? That's what we called IDT. The second one we talked about was the extreme value theorem. Okay? The extreme value theorem only works if it is continuous on a closed interval. Okay? This is the one that told us there must be at least one min and one max. Okay, this is how we kind of led off this unit, and we said if this was the absolute max and absolute min. If we have a closed interval, there is a max and a min on that closed interval somewhere. Okay, we just have to find it. And then third is our mean value theorem that we just talked about today. Mean value theorem had two conditions. What were they? Continuous and differentiable. Okay, and our conclusion from that is f prime at c equals f of b minus f of a over b minus a. Okay. Now, just a short list of things, because mean value theorem shows up in a lot of places. Okay? Slope of the tangent line is equal to slope of the secant line. A secant line is joining two endpoints. So it's what we've been doing, but it's just different language. Instantaneous rate of change equals average rate of change. It's another thing. Tangent line is parallel to secant line. Okay, and our special case for mean value theorem is Rolle's theorem. Okay, and that has one additional condition on it. The additional condition is that f of b must equal f of a. It only works when the two endpoints have the same y value, right? And our conclusion of that one is that f prime of c will equal 0 somewhere in that interval. Okay? We did it. Yeah.